Okay, so we're going to look at Chapter 3. We got Chapter 3, jump around a bit and solve some of these harder problems. So let's go ahead and get started. I'm not going to solve the first one. The only thing that might be note is amplitude. We don't really talk about amplitude. Amplitude is how high do the waves get. High amplitude is how tall is the waves. But since we don't really need to measure that, we deal with that. So, okay, I'm going to start with 3. The wavelength of some orange light is 620 nanometers. What is the frequency? We need a simple equation that converts these two. So we're going to go ahead and do that. The equation is C equals lambda nu, which states that the speed of light is equal to the wavelength times the frequency. So speed of light is 2.998 times 10 to the 8th meters per second is equal to the wavelength, 620.0 nanometers, times the frequency, which is going to be in inverse seconds. So I'm going to need to get that to the other side, but I also need to get this into the correct units. Meters and nanometers are not currently canceling, so I need to convert nanometers into meters. So there is 10 to the 9th nanometers in 1 meter, which means this is 6.200 times 10 to the negative 7th meters. So 2.998 times 10 to the 8th meters per second divided by 6.2 times 10 to the negative 7th meters is going to give me my frequency. Now, big number divided by a small number, you expect a bigger number. 9.8 second E8, but I'm going to put it in the proper sig fig notation, so I will not risk getting it wrong. So you should get 4.8, we'll say 35 times 10 to the 14th. So please note that is a bigger number. And that's what you should expect. That's what you should expect with dividing a big number by a small number. Jumping to problem 4. Problem 4, another one before we move on. Certain shade of blue frequency has a blue has a frequency of 7.34 times 10 to the 14th hertz, which is equivalent to an inverse second. What is the energy of this, given that Planck's constant is that? So once again, this is a pretty straightforward one, but let's make sure we know how to use our equations. Energy is equal to Planck's constant times wavelength. So 6.626 times 10 to the negative 34th joules seconds times 7.34 times 10 to the 14th inverse seconds should give me joules. A super ridiculously small number times a big number that's not quite as big should give me still a pretty darn small number. So 4.86 times 10 to the negative 19th joules. I just set that up, and most visible light is actually going to be in that 10 to the negative 19th range. Most visible light, meaning the colored light, red, blue, whatever. So I'm going to skip ahead to problem number 8. These are the hardest ones, just if you don't understand what it's asking for. So when we put the orbitals in, we start with 1s. We start with 1s, we go to 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So, which of these are possible? 1s is possible, 2s, 3s, all those are possible. 2p, 3p, that's possible. But F doesn't show up till row 4. D doesn't show up till row 3. It is impossible to have a half a row. So those guys are impossible. The same thing here. Which of these guys are allowable? No. So the rule is n could be any value. L can be up to any value from 0. So n is any number. L is any value from 0 to n minus 1. And then m sub L is any number ranging from negative L to positive L. Any true value. Any true. And then m sub S is only plus 1/2 or minus 1/2. That's the spin of electrons. So looking at which of these guys are allowable, when n is 3, a value of 1 is allowable. And since L is 1, m sub L can be negative 1. So that's allowable. So first one is allowable. When a row is 2, 1 is allowable, thus 1 is allowable, but m sub S cannot be 0, so not. When n is 3, negative 1, no. L cannot be negative, so we're going to skip that guy. When n is 4, the max allowable guy for L is 3. So no, that's not allowable. N is 2, L can be 2. When n is 4, L can be 2. But m sub L can never be greater than L, so no. 5, 3, 3, 1/2 allowable. As I said, this is one of the trickiest ones because you're trying to look at these stupid rules that a numerical representation of what orbitals exist. And we don't spend a whole lot of time on that, which is why I'm working through this guy. So remember, n can be any number, but L has to be at least 1 less, but positive or 0. M sub L cannot be greater than L, but it can be any number, positive or negative. And m sub S, which is the spin of an electron, can either be up or down, but it can't be 0. Now looking at that, so that was 9. I'm going to skip ahead to 12. Just an example, full electron configuration. So what we got to do, we got to calcium. Calcium is element 20. So that's row 4. So I'm just literally going 1s2. I have to do 2. Okay, I have to. Dang it. 1s2. 2s2, 2p6, 3s2, 3p6, then 4s2. So that's because that's where that's at. going the other way. I'm going to look at 14 real quick. Or 13 real quick. Based on this valence shell, this outermost level, what is the element? So 4s2, that's row 4, goes, so 2 elements in, 3d10, that's 10 more elements in, 4p6. So a total of 18 elements across. So remember, calcium we just saw was 4s2. 3d10 puts it at zinc. Then 4p6 puts this at krypton. But if I did 4p3, that would have been at arsenic. So just pay attention to where it says it is. Do a couple more. Complete the electron configuration. So this is condensed for nitrogen. Condensed, which means we're only showing the valence shell. Nitrogen is in row 2, so I'm showing helium, which is row 1. So the 2s2, 2p, nitrogen is the third element in, so 2p3. One more, and then we're moving on. How many elements does cobalt have in its 3D subshell? So just looking at that. 3D. Cobalt is element 27. Calcium is element 20. So it has 7. It's the 7th element into the D. So 7. Now I'm going to jump to the dot cam to show this. They say how many electrons are paired versus unpaired. There are 5 orbitals in the D. So I'm putting in the D. 1, 2, 3, 4, 5, 6, 7. So we have 2 sets of paired electrons, 3 unpaired electrons. So the number of unpaired electrons are 3. That's how I go about doing that. So we're going to jump to problem 21. This one I only do because sometimes they can be a little tricky. Arrange the elements according to the first ionization energy. Okay, I'm going to actually skip this one because there's not actually a trick to it. Right now, these guys are your highest ionization energy, hardest to ionize. The further down the table, the easier they are to ionize. So the lower the ionization energies. Sometimes there is a trick that they might pull. Okay, we're going to look at this guy. So, a space probe finds a new element. Here's the ionization energy. So we're looking, where's the big jump? We go 0.5 goes to 1. That's a small jump. Then it goes from 1 to 4. That's a pretty big jump. And then 4 to 5, 5 to 6, 6 to 7, almost 8. And so where's the biggest jump? Between 2 and 3. So it can lose 2 electrons easily. Hard to lose a third. So 2 electrons means it's in group 2 valence electrons. So I'm looking for where the biggest jump. The 1 to 4 is the biggest jump. Okay, now this one, I'm definitely doing this one to end it off because elements according to electron affinity. How much they want to gain an electron. Generally speaking, as we move to the right and up on the periodic table, the electron affinity goes up. There is an exception. There's plenty of exceptions, but generally speaking, if they don't need electrons, they have no good electron affinity. technically helium is the furthest right and the furthest up. However, helium has 2 valence electrons. It needs 2 valence electrons, so it's going to have the lowest. So boron going to have higher electron affinity. So we want most energy absorbed by gaining an electron, most energy gained. So energy cost versus energy gained. Fluorine really wants that electron. And so it's going to release the most energy when it gains that electron. So you might be tempted to put the helium Fb, but it breaks that model because it is a noble gas and it doesn't want any electrons. But that's where we're going to stop. We are all done. That's all I wanted to go through. I just wanted to kind of give you some guidance on some of these trickier ones. Okay, have a good day.